Today we're going to learn about performing function operations, like adding two functions or subtracting, multiplying, dividing, and composition, putting a function inside another function or inside itself. Given f of x is 5x and g of x is x plus 2, let's find f plus g of x. This also means f of x plus g of x. So we're going to add the two functions. Combine like terms, and you have your answer. F minus g of x is just f of x minus g of x, so subtract the functions. Distribute and combine like terms. And you have your result. F times g of x is f of x times g of x, so multiply the two functions. Distribute to simplify. F divided by g of x would be dividing f by g. Because not all three of these terms have a common factor, there's no more reducing or simplifying we can do for this one. The last one is a circle, not a dot, a little circle. This is f composed with g of x. You could also write that as f of g of x. That means we're going to plug in the entire g of x function into the input of f. F of x is 5 times x, so f of g of x will be 5 times g of x. So f composed with g of x is 5x plus 10. Keep in mind, that means that if you compose g with f, you will get a different answer, because that would mean plugging in f of x into each x in g. For number 1, let f of x equal 3 root x and g of x equal negative 10 root x. Find f plus g of x and state the domain. When we're stating the domain after performing function operations, we need to be at least as restrictive as each of the individual functions. The restrictions of f of x, the square root radicand, cannot be negative. So for f of x, our domain is restricted to x greater than or equal to 0. And the restrictions of the g of x domain would be the same. The radicand, which is x, has to be greater than or equal to 0. So let's find f plus g of x by adding the two functions. We can combine these like terms. 3 root x plus negative 10 root x is negative 7 root x. Then we'll check for any additional restrictions for the domain of f plus g of x after simplification, and the domain here also is x greater than or equal to 0, which is not more restrictive than the domains of f and g individually. Therefore, the domain of f plus g of x is x greater than or equal to 0, or in interval notation, 0 inclusive up to infinity. To evaluate the sum at x equals 4 algebraically, we'll plug in 4 for x into the f plus g of x function. After simplifying, you get negative 14. To evaluate the sum at x equals 4 graphically, we'll graph the sum of these two functions and find the y value when x equals 4. And if we had a large enough graph, we could see where that is, but you actually have a function on a graphing calculator that allows you to do this. To do this on a graphing calculator, you'll plug in y1 is equal to negative 7 root x, and then graph. From there, you can calculate the result at any x value. And the calculator will also tell you that the answer is negative 14. For number 2, we have this polynomial for f and this polynomial for g. The domain of f of x as a polynomial is negative infinity to infinity, and that is also the domain for g of x. Because we know the sum or difference of two polynomials will always result in another polynomial, we know the domain of this difference of functions will also be negative infinity to infinity. Go ahead and evaluate f minus g of x. As we said before, the result is a polynomial, and the domain of every polynomial is negative infinity to infinity. To evaluate the difference when x equals negative 2, plug in negative 2 into the result of part A. And the result is 3. For number 3, find f g of x. That is f times g of x. And state the domain. The domain of f of x, a parabola, is negative infinity to infinity. The domain of g of x, root x, is 0 inclusive to infinity. So the domain of f times g of x has to be at least as restrictive as 0 inclusive to infinity. Now multiply the functions. We could have one base of x with a rational exponent. That's x to the 5/2, or root x to the power of 5. We already know that the domain of root x has the restriction of 0 inclusive to infinity, and that's already the restriction of g of x. So the domain of f times g of x is also 0 inclusive to infinity. To evaluate the product when x equals 4, let's plug in 4 for x. And once you simplify f times g of 4, you get 32. F of x equals 6x is a linear function, so the domain is negative infinity to infinity. G of x is x to the 3/4, which could be rewritten as the 4th root of x cubed. The restrictions for a 4th root are the same for a square root, so your domain must be 0 inclusive to infinity for g of x. Now find f divided by g of x and state the domain. When you simplify this, you have 6x to the 1 divided by x to the 3/4. Because you're dividing the same base of x, you'll subtract the exponents. Because f divided by g of x still involves a 4th root, but nothing else that would add further restrictions, then our domain for the division of these functions is the same domain as g of x, 0 inclusive to infinity. Let's evaluate the quotient when x equals 16. The 4th root of 16 is 2, so this simplifies to be 12. For number 5, we have two polynomial functions. For part A, find f composed with g of x. Because f of x is x squared plus x, you have two inputs of x. In each input of x, you will need to plug in the entire function of g. F of x is x squared plus x. Expand the binomial squared to be a perfect square trinomial, and continue simplifying. Making our result for f composed with g of x, also known as f of g of x, 16x squared plus 20x plus 6. Now we're going to compose g with f of x. G has one input of x. It's 4 times that input plus 2. Now that input will be the entire f function. Now simplify. And now you've found g of f of x, or g composed with f of x. In order to find f composed with f of x, we will plug in the entire f of x function for each x in the function of f. Now expand and simplify. Making f composed with f of x, x to the 4th plus 2x cubed plus 2x squared plus x. Go ahead and find g composed with g of x on your own, then press play to check. And g composed with g of x is 16x plus 10. Gog. To find f composed with g of -1, we'll plug in -1 into our answer from part A. So f composed with g of -1 is 2, and for part F, we'll plug in 0 into the result for part D. And that is how you perform function operations, including composition.